All right, welcome back for the next one. In the previous video, we read this problem, but we want to reread it again. So you have here, Carol is pushing a 25 kilogram wood box across a wood floor at a steady speed of 2 meters per second. So here is what's happening. Let's see. So here is the wooden floor, and here is the wooden box, and the box is moving at a speed of 2 meters per second. V is equal to 2 meters per second. That means the acceleration is simply equal to zero. Because it's constant speed. And the box is, let's say, is moving this way, right? It's moving that way. So, what are the forces involved? Well, I know that it's on Earth, so there has to be the force of gravity, and it's equal to mg. I know that it's in contact with the floor, so there has to be a normal force. It's in the upward direction. And there is friction in this case, and friction always goes opposite to the motion, so there is the force of friction. What kind of friction is it? Well, the box is sliding on the floor, so it has to be the force of kinetic friction. And it's in this direction. And so, if this was the only picture, then there is a net force on the x direction, so the box has to slow down. So if it's moving at constant speed, or constant velocity in this case, along the line, so somebody has to be pushing it this way. So Carol is pushing it this way. I'll draw that force vector this way. So here is Carol's force, the force by Carol, that way. Okay. I don't know how much is this, what this force is. I will draw my axes. Here's the positive x direction. Here's the positive y direction, as usual. So we would say the net force in the, try to work a little bit here, and then go on. I know that the force of friction depends on the normal force, so I need to find the normal force first. So first, in the y direction, the net force in the y direction will equal to the mass times the acceleration in the y direction, but the box is only moving along the x direction. So there is no acceleration in the y direction. The box doesn't go up nor sink into the floor. So that's a zero. The net force in the y direction consists of two forces. There are two forces that have a y component. That is the normal force and the mg. So the normal force upward minus the mg, because it's downward, equal to zero. And therefore, the normal force will equal to mg. Very often, the normal force is simply mg. Not always, but very often that's the case. And so that's the normal force. And therefore, immediately I would say, all right, then the force of kinetic friction is simply equal to uk times the normal force, and that is equal to uk times m times g. That's the normal force. That's the force of friction. And if you like, you can get a value for it. So the force of kinetic friction is simply equal to mu k times mg. So that is, what's mu k here? It's 0.2. 0.2 times the mass, that's 25 kilograms, times 9.8. 9.8, and I get what? A fifth of 25 is 5, and 5 times 9.8 is 49. So it's 49 newtons. 49 newtons. That's the force of kinetic friction. All right, how about I would like to know what this force is. You probably can guess. It has to equal to the force of kinetic friction, so that the net force in the x direction is 0, and the acceleration is 0 also in the x direction. So let's just do it more formally. By the way, this is, if you like, this is part A. It's the first part, this part. We didn't do this part yet. How many, if she stops pushing, we'll get to that in a moment. So let's continue. The net force in the x direction now, let's do that separately. will equal to the mass times the acceleration in the x direction. We're told, yes, it's moving in the x direction. However, it's moving at a steady speed. So the speed is steady. It means the acceleration is 0. And therefore, the speed is steady and in a straight line. It means the velocity is constant. It means the acceleration is equal to 0. Right. To 0. The net force in the x direction consists of two forces. This force F, with which Carol is pushing, I'm going to call it, it would be positive, just F, because it's to the right. And the force of friction is to the left, so put F minus K. So it'll be like this. Capital F minus Fk will equal to 0. That means the force with which Carol is pushing will equal to Fk, and the force of kinetic friction is equal to 49. 49 newtons. Okay. That's it. How much force does Carol exert on the box? 49 newtons. Now let's go to part B. Part B, if Carol stops pushing, what changes in this picture? Well, this F here disappears. The force of friction will still be there. As long as the box is moving, there will still be force of kinetic friction. The normal force is still upward, mg is still downward, and there is no motion in the y direction. It is still, therefore, the normal force minus mg equal to 0, and the normal force is still mg, and so the force of kinetic friction is still mu k mg, and it is still equal to 49 newtons. So let's find out then what the acceleration will be in the x direction in this picture here without the force of, without the pushing force. So here is the mass again, here is the normal, here is the mg, and then here is the force of kinetic friction. What's missing is her push. Okay. So I know that the net force now, so this is a different problem now. The net force in the x direction will equal to the mass times the acceleration in the x direction. So now the acceleration in the x direction will no longer be 0, because once she stops pushing, the box will start to slow down and come to rest. And so there will be an acceleration and it's negative. So we would say, all right, the net force in the x direction is the force of kinetic friction, and that's equal to ma in the x direction. And so the force of kinetic friction is actually, I have to put a minus sign here because it's negative. And the force of kinetic friction is, so it's, you have minus mu k mg, and that's equal to ma, the acceleration in the x direction. So I have the mass cancel, and so that means the acceleration in the x direction will equal to negative mu k times g, and so that is negative 0.2 times 9.8. So how much is that? That would be, I believe, 1.9 newtons. Or 1.96 maybe. I'll just use my calculator. Sometimes I can think quick, so times 9.8. Yeah, 1.96. So that is right. So it is negative 1.96. The negative sign means the acceleration is to the left. Meters per second squared. But they didn't ask for the acceleration. They say, how far will the box go before coming to rest? So here, the box is going at a speed 2 meters per second, and then eventually it comes to rest. So we got V initial, we will write this equation, V final squared minus V initial squared is equal to 2 times the acceleration times x final minus x initial. We would like to know how far it will go, so this is just the distance it will move. The final position minus the initial position, that's just the distance. This is just the distance. I can call it d if you like. So d, or before I continue, the final velocity would be 0 because it comes to rest, minus the initial velocity squared, that's 2 squared, which is 4, equals to 2 times the acceleration. The acceleration is negative 1.96. And then this is the distance that it moves. And as you see, minus and a minus will go away. The distance will just be positive. And so D will be what? 4 over 2 times 1.96. That's almost 2 times 2, which is almost 4. So it would be what, 1.0 something. 1 point what? Okay, let's do it times 2. Approximately 1.02. 1.02 meters. So the box will slide for about 1.02 meters and then it comes to rest. Okay? And yeah, so that's that. And so this is how you tackle kinetic friction. So the next problem I would like to do here on the next board is a problem of static friction. A problem of static friction. I would like to do it in 3 pieces, into 3 different problems. Example, 3 different cases. Example. Let's say we have a box, a 10 kilogram box rests on a horizontal surface. The coefficient of friction I'll put the coefficients of static friction, static and kinetic friction, static and kinetic friction are mu s equal to, let's say, 0.3 and mu k equals to 0.25, right? Notice the coefficient of friction is just a number, right? And so let's do case 1. So here is case 1. So here's the box. It's on this surface. So my first question is, as the box rests here, it's not moving, so V is 0, it's at rest. V is 0. What are the forces? Let's write them down. The forces will be, of course, you get mg, and of course you get the normal force. Now, if I ask you what's the force of kinetic friction, you will say 0. What's the force of static friction? You would say also it's 0. Because if you had a kinetic friction, first of all, you don't have kinetic friction unless there is relative motion, so that's not even possible in this case. Static friction, remember, it takes values between 0 to some maximum value. This box is not moving. So the coefficient of static friction in this case is equal to 0. I'm sorry, not the coefficient. The force of static friction is also is equal to 0. So Fs is equal to Fk, and both are equal to 0. So this case is, I guess, boring. So case 2, we'll make an incline. We'll take our box and we will incline the surface to some angle, let's say 10 degrees, right? 10 degrees. Here's our box. And here's our box. So the first question is, will the box move? And the second question is, if it does, if it doesn't, at what angle do we need to tilt it to start moving? So before we do that, we have to analyze the following. So we'll say there is the force of gravity, it's mg. And as usual, we'll take this to be the x, this to be the y direction. So the normal force is in this y direction. And this the force of gravity would have 2 components. One of them is, this is the force of gravity here. So one of them will be this one, the y component of the force of gravity, and it's mg cosine theta, but this downward direction. So it's mg cosine theta, and there is this part here, the mg sine theta, and then there is the force of friction. If it started moving, it will be kinetic. If it has not moved yet, it will be static friction. So we have to figure it out. We have to figure out whether it has moved or has not moved. So first, let's figure out what the normal force is. The force of gravity has a negative component in the y direction. The normal force is this way. So we conclude that there is no motion up and down. If there is motion, it will be along the incline. So the net force in the y direction will just be is equal to 0 because there is no acceleration. And so that means the normal force that's in the positive direction, positive y, minus the mg cosine theta because it's this way, mg cosine theta equal to 0. That means the normal force will equal to mg cosine theta, cosine of 10 degrees. And so the maximum, the force of static friction, the maximum value will be mu s times the normal force. And so let's multiply them and see what we get. Because if we have exceeded the force of static friction, the box will be sliding. If we haven't, then the box will not slide. So let's see what the force of static friction will be. Mu s, we said 0.3. And then the mass is, how many kilograms was it again? A 10 kilogram box, 10 kilograms, right? Mg cosine theta. Gravity is 9.8, and then times the cosine of 10 degrees. And so we get the maximum static friction, max, for this 10 degree angle. Let's calculate it. 0.3 times 10 times 9.8 times the cosine of 10 degrees. And I get 28.95, about 29, 28.95. So approximately 28.95 newtons. So the force of friction, the force of static friction can take values, the force of static friction can take values between 28.95 and 0. So when it was flat, the force of static friction was 0. When you tilted it this way, there is an mg sine theta, so the force of friction will try to counter that. So let's calculate the mg sine theta and see. If the mg sine theta is less than this value, then the force of static friction can keep up with it and prevent it from moving. So let's calculate the mg sine theta. So we got the mg sine theta will equal to, the mass is 10, g is 9.8 times the sine of 10 degrees, and so that equals to 10 times 9.8 times the sine of 10 degrees. 17, about 17, 17.01. 17. Well, the force of static friction will happily accommodate for this. So it will increase, and it can take values up to 28.95. So 17 is in the range. So therefore, the object is not moving. So this object still has not moved. So that's okay. All right. So we concluded the object has not moved, and that the acceleration is 0, and everything is okay. So here is the next question. I would like, eventually, right, if I tilt it and tilt it and tilt it, the object will start to slide. At what angle will it start to slide? Well, it will start to slide when the force of static friction has reached the maximum value. So if you increase the angle a little more, the force of static friction cannot keep up with the mg sine theta, and it will fall. So let's look at it. So for case 3, here's the question. Case 3. At what angle will the box start to slide. It will start to slide when the static friction has reached the maximum, and then it breaks loose. The box breaks loose, and then it becomes kinetic friction. It just starts to slide. At what? So it's a question. Well, let's look in the x direction. In the y direction, it's still the normal force minus mg cosine theta equal to 0, so the normal force is equal to mg cosine theta. In the x direction, I have two forces. I have mg sine theta in the positive x direction and the force of static friction to the left. So the net force, the x direction. I would like the acceleration to still be 0, right? The acceleration to still be 0 because it hasn't started moving yet. And so what are the forces? The mg sine theta, right? Mg sine theta minus the force of static friction equal to 0. And the force of static friction, so it will start moving slightly after we have reached that maximum angle, and slightly after we have reached the force of static friction. If we exceed it, then it will start to move. So let's see. So I have mg sine theta. Oh, I should write here the force of static friction because we have reached the max, so put maximum. So minus mu s times the normal force, but the normal force is mg cosine theta equal to 0. And so the mass just cancels on both sides. And then the g also cancels. And so take this to the other side. So you get mu s cosine theta equal to sine theta. Divide both sides by the cosine. So you have mu s equal to sine over cosine, which is tangent theta. So you get mu s equals to the tangent of theta. So that's the angle at which it will start to move. So theta will be tangent inverse of mu s. So that's tangent inverse of 0.3. Right? Mu s is 0.3. And so let's see at what angle that is. It would be more than 10 degrees. So tangent inverse. Let's see, tangent inverse of 0.3. So that's about 16.7 degrees. So 16.7 degrees. So at 16.7 degrees, the object starts to slide. Starts to slide down. Okay? So that's when it will start to slide down. And I should probably just let this one go. And then we will get to a different problem. I was going to continue with it a little more, but I think in the homework we'll do more about friction. Okay, so the next force that we're going to consider is the drag force. And the drag force is, so imagine you have a piece of paper that's falling under the influence of gravity. And so it will experience drag. So it's not going to fall at a constant, at a free fall. In fact, it will experience some drag. And the drag will depend on a few things. The first thing it will depend on is how fast is the object moving. It will depend on the surface area or the cross-sectional area of the object. And it will depend on the density of the material in which it's moving and on the drag coefficient. So let me just summarize the force of drag and then write it down and then tell you how it's going. Right? So let me write it down. So it just has the symbol F, drag. It's equal to 1/2 the drag coefficient, density, the area, and v squared. So let's try to explain what each of these means. So let me just come here. And so let me just show you here. So for example, see here the drag coefficient. First of all, let's start with the speed is the speed of the object. The faster the object moves, the more drag it will experience. And in fact, they're saying the drag is about, basically, this is an experimental force, an experimental formula. So it depends on the speed square. So if you're driving in your car and let's say the air is still, the faster you drive, the more air resistance you experience. And so if you drive twice as fast, you will experience 4 times the drag. The surface area, so if you have, many times people joke at different cars, they say it has the aerodynamics of a refrigerator, meaning the car is kind of boxy and it will experience a lot of drag. So if the car looks like squarish like this, it will experience a lot of drag. So it depends on the cross-sectional area of the car. So let's say the car has a cross, the object has a cross-sectional area A, like so. It could be, the object could be a sphere also, in which the area that faces, let's say it's moving this way, the area that faces the air, in this case, that faces the dragging thing is the area that's facing the projection. So it's pi r squared. But so if it's just a box, the drag coefficient would be something. If it's maybe if it's a cylinder, the drag coefficient will be something else. Drag coefficient will be something else. So if it's a cylinder, let's say, in all of these cases, let's say they're moving like this, each of them has a different drag coefficient. So let's say again, the area is just how much area is facing, and then this coefficient C will depend on the shape itself, on the aerodynamics of the thing. So if it's a cylinder, if it is a cylinder that's moving horizontally, then if it's moving like this, then the drag coefficient is about 1.1. If it's a sphere like this, let me just look up the value. Then it will be 0.5, 0.5. In this case, for example, if the radius here is r, then the area is pi r squared and c is 0.5. For this one here, what would the area be? Well, it will look like, it's like a box that looks like that, right? So if this is height h and this is radius r, so it would be 2r for the cross-sectional area times h, 2rh, I believe. So let me just double check that. 2r, yeah, times the length of the cylinder, or the height of the cylinder. The height of the cylinder is from here to here. That's h. Okay, and then rho is the density of the material in which you're going through. So if it's a dense material, let's say the density of air is typically about 1.3 kilograms per cubic meter for air, typically at standard temperature and pressure. So it's typically approximate for air in which we're usually moving. We're not moving in water or something, it will be much denser. So in air it's 1.3, approximately 1.3 times 10 to the, just 1.3 kilograms per cubic meter. Okay, per cubic meter. So let's see how we can use this. So let's say you have a car. I'll just write down the problem here. So you have they say the typical profile for a 1,500 kilogram passenger car is that the car looks. So here is the car. How do I draw a car? Like, so let's say the car is. Say the car is moving this way. So the coefficient, this C, will depend on how you shape the car, how nice, smoothly it's made, but then the area is still the cross-sectional area. So let's say the car, the area that's facing looks basically something like that, and it is 1.6 meters wide and 1.4 meters high. So let's say 1.4 by 1.6 meters this way, and it's moving like that. That's the area that the car faces with. And let's say C is 0.35, just 0.35. And they say at what speed, so let me say here, at what speed is the drag force equal to the rolling friction force. So the car is 1,500 kilograms. The mass of the car is 1,500 kilograms. All right. And in fact, let me continue this problem in the next video.